Another edition of Talk Physics, where I talk, you listen, I guess. Sorry, I wish there was somebody else to have a conversation
Another
with,
edition of Talk Physics,
but they don't show up.
where I talk, you listen, I guess. Sorry, I wish there was somebody else.
Find the button. Yeah, there we go. Now I'm continuing. Anyway, so you heard that twice or something like that. Anyway, uh, yeah, my error. Probably. There's a lot of little stuff. Hard to keep track of it all. Anyway, so I just throw in a little bit of two slit stuff to start with, and then I'll just go to some general bits of conversation about why their theory sucks and my theory's great, stuff like that. So anyway, so I did get a couple of bits of video of different. That's not video. That's a still image. Yeah. There it is. All right, so two razor blades, and I just did some, just this same turning thing. And I found, so when I turned a slide, okay, it looks like this, and I turn it to make the slit smaller, you know, theoretically, doesn't do much. You can turn it quite a lot and you don't get much change. So the bit of transparency somehow causes a difference. Two razor blades, though, in a format something like this, without the hair, like this. Two slits in there. Anyway, this, you turn it, big difference, just a little bit of a turn. Now, obviously, it probably has something to do with the thickness. The metal's much thicker than the transparency, things like that. But huge difference. So I just thought, so here's some video of how easy it is to change the pattern by just turning it. So you don't even need to do this, slide the things together thing. You just need to turn it. Big difference. Oh, God, hiccups. Great. Make it a little bigger. A big difference. So now the slit is wider, and then as it gets narrower, it gets bigger, the pattern. So as I'm turning it, and it didn't take much turning. You're not talking anywhere near 45 degrees. It didn't even get near 45 degrees. And it started getting hugely wide, as you can see. So it is interesting for at least seeing how the pattern changes. So it is a good way an easy way to manipulate things to see if you can discover anything, interesting. It is a fairly good pattern the razor blades create, so, especially with the green laser. So I should be able to do something with that. Yeah. So you can see how little this card in the background, this shadow is the card I'm turning. And you can see how little I'm turning it, because obviously it doesn't get really, really small and then really, really big. So it's not, the shadow of what I'm turning is not very, it's not changing much. And you're getting a lot of change in the pattern. So big difference between, as stated. What it means, I'm not sure, blah, 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 blah. Might as well show the other video since I'm here. I believe it's in here. So this, I was just sticking a round metal impediment in front of the pattern. And it's just this weird thing where, so this is a solid piece of steel, and this thing happens, where the pattern just keeps going right through it somehow, and I'm it's a little logical. You have to do some thinking to figure out why that would be. But I mean, it's obviously treating this impediment, again, like two slits. So we're talking about something as thick as way over 1 millimeter. I mean, it's thick. If something similarly thick here, yeah, sort of like the thickness of that. The end of it's not tiny, so it was like maybe 2 millimeters, 3 millimeters across, round thing, and I have it in front of, so that the laser beams here, the target, and then there's the final target. So it's between the razor blades and the final target, and I'm just moving it around, just holding it, moving it, and like as you can see, it does consistently, no matter where you kind of put it, it does this thing, okay, where it creates another kind of pattern, but it's like I said, it's a little hard to account for it, seeing through, essentially, as if it wasn't there, essentially. But anyway, curious for something that big to create that much of an effect, because it's kind of technically too big to be doing two slit style or one single slit style diffraction. Yet it is. Anyway, it's just curious, I think. Obviously, the further away you go, the less this effect and the stronger the shadow becomes. So it really has to do with proximity. And I wasn't terribly close, but I was within a few inches, I think. Yeah, within a foot. All right, so anyway, like I said, I can't draw any conclusions yet, can't make any statements yet, I don't think. I just, to me, it just doesn't seem like a Huygens kind of event, but whatever. I'll have to argue that when I can argue that. So, a couple of retracted statements, fine. Suit yourself. Yes, no real subscriptions to talk about, so there's still little stuff going on here. Kind of disappointing because the rational whatever guy was just, his videos this week were all just subjective, objective, kind of minutia, in my opinion, on with the, this whole concept of the difference between understanding and knowledge. I put knowledge in a category where it's something like the word educated or informed. So it's like you can have an informed source or an uninformed. You can have a knowledgeable source, an unknowledgeable source. So it's just really about a volume of information, which makes something more reliable, the more knowledgeable it is. That kind of thing. But anyway, who cares? So I guess that's all. There's not much else to talk about. The Holster guy didn't do his Friday room last week, and he hasn't done any videos since. So maybe he's taking a little time off or something. So in case I have to draw anything, I guess I'll leave open the drawing program. Or maybe I should just go to the website. That might even be a better idea. Till I'm going to draw something. Might be better. And I could just point out things that are important. These are always important drawings here. The whole idea of the pressure between the electrons. And this is probably the most important kind of drawing, but people won't be able to follow along without me explaining the illustration, I suppose. So maybe we'll just go with the magnetism drawing. All right. Just such a good explanation. So, can't really read my notes because my eyes have just been terrible this week for no good reason that I know of. The way it works, I guess. With this age thing, good weeks and bad weeks. What's your opinion of imaginary numbers? Well, obviously it sounds on its surface kind of yuck. Do you really have to go there? So I guess I'd say I don't like it too much. And it's the other two words they use, when they do the imaginary number thing. They use those two really weird words. But yeah, it gets so abstract, the math, that you're almost like, is this math really work somehow? I mean, it just seems a little bit silly. But I'm not. The set stuff sort of makes sense. I can go along with the, each variable in a different dimension, X, Y, and Z, and all that kind of stuff. I get some of that shit. But yeah, the rest of it's a little bit. I don't know. Also, how can we know when you're going to stream? Well, you can't. So that's just the way it goes. Do you announce it before anywhere? No, I just don't. It really just depends on my day. Look, it's sort of reliable that I end up doing this around 12 o'clock or 12:30, somewhere between 12 and 12:30 midnight Eastern Standard Time is the most likely time I'm going to stream. But I just don't have my life just isn't ordered enough, and I don't necessarily feel reliable enough. This, it's just the way it is. Yeah, kind of. Yeah, the days are too messy. There's always interruptions. So yeah, just can't rely. I just can't say, oh yeah, 3 o'clock tomorrow. Just can't do it. Yeah. All right. So I was, well, we'll see if he says anything. It makes sense. Some of the best things are unplanned. Well, I don't know about that, but whatever. That sounds a little cliche to me. I don't. Every cliche probably needs to be examined under a microscope, and you'll find flaws in it. And you'll say, "Yeah, we probably shouldn't use this cliche either. It's broken." Anyway, all right. So as I've explained, regular physics has a couple of glaring problems. One of them is this energy issue that I've brought up a few times. And the one you could probably see it the most obvious in is the magnetism one. Okay, is they got no explanation for this, this magnet, jumping, across space. Yeah, they got no explanation for how it does that. Where the energy comes from. No energy gets burned in here. No energy gets burned in the thing here. Nothing loses mass. Yet, energy takes place. Something, movement takes place. And there's no explanation for, what usually has to happen, in this conservational sense for there to be movement. And that is, you have to release pressure from some system where you've stored pressure. And that's another key word here is pressure, because there's so many, I don't agree with anything the electric universe, and their whole concept of thing. I don't agree with it, but in a sense, they're onto something. Okay. And even Ken Wheeler every now and then says pressure mediation. He'll say those words. And, bingo. Because that's what all this is all about, is nothing really moves until something pushes it. And what pushes it is pressure, the stuff. And so in a sense, for the electric universe, they're right in a sense to say it's all voltage, technically, because that's essentially what pressure is. It's voltage is essentially a kind of pressure, and that is exactly the same kind of pressure running through a wire. It's really the same force moving those electrons that little tiny bit of distance, but essentially moving a bunch of force that distance, that pressure, transferring pressure from one point to another is the same thing as moves planets, and it's the same thing that moves the magnets. It's all about this pressure thing. Yeah. See, but even now I'm getting caught in my own cliche, because clearly the other part of the pressure thing is the idea that you have to get this segregation thing, this idea that um, the pressure is either all or nothing in terms of what force is interacting with what kind of matter. So we're back to charge again. All right, so that so this is a very jumping from place to place kind of what do I call the videos? Overview video, except it's bouncing. All right, because to really understand what's happening in the universe, you could say, okay, everything's the only stuff that's actually moving. This is like a sort of an argument in the universe are the little things moving the speed of light. And as I pointed out, stuff can look like it's not moving when that speed of light stuff is going in a circle or a square or back and forth. So going back and forth looks like you don't going anywhere if you think about it. You just end up back at the same point all the time. It's the same points. So you don't travel anywhere. So it looks like you didn't go anywhere, which looks like you don't have any energy. All right, so that's really all there is that little stuff moving. And all you're really talking about is how does it do that? So the catch is that what seems quite obvious is it doesn't interact with each other very well. So you can't shoot photons at photons and have them bounce all over the place. You can't reflect them off of each other. You can't do that. You have to stick something in between. So if I have two laser beams, a red one and a green one pointed at each other, they'll just go right straight through each other. But if I stick a piece of matter in between them, well, then they can fight. Then they can push on each other, so to speak. Then you can move something by having twice as much energy on one side as you have on the other side, like a water hose. So if you think about it like water hoses, you can think that the water doesn't interact with water, but it will interact with everything else and push it. And everything's just going to get pushed by whichever the most water is coming from. If you want to think in ethery kind of terms, medium kind of terms. But the problem with mediums is that they don't fix the problem I brought before, which is there's no energy. Okay, so a dead ether will not push the earth into the sun. So just, bucket of sand that isn't doing anything can't push two things together. But if you make those bits of sand, you'll give them all random directions, just let them randomly go in different directions at some set speed, then any two things I drop into that sand that are material, that is, that are hit by sand, will end up eventually colliding into each other. They will, they'll either move to the side of the bucket, stick to the bucket, or they'll move into each other. And that's a physical fact. That's physics. That's sort of proven. We can say that with certainty, that's the effect. So if you're going to have an ether, you have to kind of realize that your ether needs energy in it. It needs to be already pressurized. Moving stuff through it is fine, but that still doesn't explain how planets move into other planets, and it doesn't explain how magnets move into other magnets. It doesn't help at all. And if you start doing all this crap, about how see this picture of a magnet over here, okay, you can see these are all little straight lines coming out. And I just used the curved lines to show those are the magnetic lines of force, but nothing is moving on those lines. Those are just to point out that if you put something ferrous next to that magnet, they'll line up on those lines because they all become repulsive. Now I found a good example of that today, actually, when I was playing with this. So I did some needle experiments. I have pictures of those, but I'll show them next time. But anyway, I put 3 needles on this magnet, thinking, oh yeah, I can just put them at any set distance and everything will be fine. Well, I didn't think about it. But what happens is the needles all become magnetic and they repel each other because they're all magnetic in the same orientation. So you can't make them go close together. They all just move apart. So it doesn't work as a magnet holder. The magnet doesn't, I mean, as a needle holder. So the magnet doesn't work as a needle holder because the magnets do exactly what the little ferrous materials will do with the magnet is they'll all repel each other. This will be all magnetized by the original magnet in the opposite direction, and they'll all oppose each other. So I've already sort of explained that in past videos, and well, I've explained everything in past videos. So, so like you just said here, pressure from the ether ? That would be great, but then none of the ethers described by people have pressure in them. So that's their big failing. So there's no, again, they don't have a source of energy for the two most obvious energetic events in the universe: galactic movement, the sun, the stars, the moon, asteroids. All of that movement is unexplained, and magnets, completely unexplained where the energy comes from. So ether doesn't do anything to resolve the biggest problem with conventional physics or non-ether. But clearly their theory is ether. So let's not, I mean, as much as, keep going, strangling words, having this concept, but I mean, clearly conventional physics they're just using the word field as a substitute for the word ether. And they're clearly obsessed with waves, just totally obsessed. So clearly they are arguing for an ether theory, and for whatever reason, they're afraid to use the word ether. Chickens. But that's what it is. Even the whole idea of calling it bent space, a bent nothing. Space is supposed to be nothing. You could say bent ether. That would make some sense. But bent space? Come on. All right, so now we've jumped. All right, so what I was trying to get to was just all these little force bits, or what everything's made out of, just these little black and red bits moving the speed of light. And the matter bits are actually those bits. They're just not free. So they can be in two forms: free and not free. Trapped. You could argue are stuck, going back and forth. It's the same thing. So if I said an electron was, 10 force bits, and all they do is go back and forth. Okay, that's all they do. They go back and forth this way, and this way. I could say that. Now the trick is I don't think electrons are three-dimensional objects, because they can't store velocity. That is, they can't hold it. They lose their velocity. So when you stop pushing them, stop hitting them with more stuff from one side than they're hitting them from the other side, they stop moving. Where matter keeps going. You throw a wrench into space and it'll keep going. As long as you overcame gravity, it'll just keep sailing along. Presumably. Not proven, but it'll substantially maintain a tremendous amount of velocity. It won't lose much, if it loses any. Right. Okay. So the real point is thinking in terms of dimensions. So I've been over this before, but it's sort of an important little point to make, is that all the force bits moving the speed of light, they essentially have no mass in any other dimension but the one they're traveling in. And you can argue they only have mass in 1/2 of that dimension, so one sub-dimension. So you can say there's 6 sub-dimensions, forward, back, up, down, left, right. And the little force bits obviously just don't have any substance sideways. They can't hit one, can't feel one, can't touch one, can't influence one. The only thing it has mass in, the only thing it has momentum in, is one-dimensional. It's a one-dimensional object in that sense, because it can only impact something. It can only create an impact in the direction it's heading and in the dimension it's heading. And that's it. Now, you could argue that electrons can do 2 dimensions. So they can do this one, the forward, back, and they could do up and down or left and right, one of those, any two of that combination. And that would explain their what's called spin, in the sense that you could sort of understand that, up and down spin kind of nonsense would be something like an electron that is functioning in going this dimension, or it can go this way. So it can go forward and back, and it can go left and right. And then a different electron could go this way, up and down, or forward and back. And then obviously you can have one that goes left and right and up and down, but doesn't go forward and back. So you can have, and they call that, you could argue that could be what they're calling spin. So they're all the same in a sense. They just have an orientation, a dimensional orientation. And that sort of explains the phenomenon of magnetism, in the sense of when the electron moves, it radiates a force perpendicular to its movement. And either one of the dimensions would be perpendicular, but each electron has its own orientation. And you could say that there also can be filtered for that orientation. All right, so, but it's just a way of thinking about it. So the force bits are, you could think, one-dimensional. The elemental atomic bits, that is the protons and the electrons. The neutrons are just a proton and an electron. So they're out of the equation now, in terms of elemental. They're made of something, where the electron and the proton are elemental. Now they say they're made of quarks, but let's not play with that stupid word. The real point is, quarks could just be these force bits. So let's not even play with quarks. All right, so, but the point would be is that, so the force bits are one-dimensional. The elemental atomic bits, the electron, the proton, the two charge elements. So remember, the force bits come in, you could say, yellow and silver. Okay, silver or yellow, black and red, whatever, square, round, doesn't matter. And the matter bits, the elemental ones, protons, electrons, come in the same orientation or character. And the two of them interact inversely. So the black force reflects off the black electron force, reflects off of electrons. Proton force reflects off of protons, and proton force leaves perpendicularly from electrons, and electron force leaves perpendicularly from protons. Now, with that simple mechanism, you can end up creating a tremendous amount of pressure variation when a force comes in. So when a mixed force comes in, as you can see in this image, I guess I'll switch this thing. I don't know how it's recording, so I guess I won't switch it. Oh, look at the recording. Sorry, I'll take a little time out and I'll figure out which way. Yeah, so it's oriented this way in the recording. So that must be, yes, it must be the same for you as me. So I'll reverse this and that should be better, I think. Because now when I point over there, it'll be over there. Yeah, so that makes things a lot easier when it's over there. When over there is over there, it's a lot easier. Anyway, all right, so when you have mixed force coming in, it's doing in the top here. If it's black, it would reflect off that little electron, and the electron would move down. If it's red, it would leak out the sides. Okay, and the same thing's happening to the proton, and you can sort of understand that in between, if it was two electrons, then the black force would be trapped, and it would be creating reflections back and forth, that would be creating pressure. But none of that can happen because the black force leaks out of the proton, and all the red force, that can't get stuck because that all leaks out of the electron. So all the force leaks out of here. So you have no reflecting pressure. And so the two objects will move towards each other. And that is illustrated more precisely somewhere in here. Yeah, so you sort of get it here. Obviously, when you move the two electrons together, the little bits caught would be bouncing at a higher frequency. So that's how light is created at different frequencies. The frequency of the light is dictated by how close the electrons are. Closer the electrons are, the higher the frequency. Further apart they are, the lower the frequency. Obviously, the closer they are, the higher the pressure. Okay, the higher the voltage. That's why there's a relationship between voltage and the frequency of radiation emitted, meaning that with enough voltage you can create like X-rays, because the voltage is creating pressure. The pressure is pushing the electrons closer together, which means the vibrations are faster back and forth, which means when they get let loose, they're let loose at a higher frequency, closer together in time. All right, so anyway, the point I was leading to is force bits, one-dimensional, elemental atomic bits, two-dimensional, atom, three-dimensional. So it has bits essentially moving in all the dimensions, all three dimensions, any three dimensions, no matter how you want to turn them or twist them. And so it's the first full three-dimensional object. Or you could say the helium nucleus is the first three-dimensional object, because it has a structure that provides that the proton and the electron combinations are combinations that have elements moving in all three dimensions. They have pressure in all three dimensions. And therefore, they're able to construct mechanisms to keep moving, to trap energy. In a sense, the energy comes in, it gets trapped in the atom or the nucleus, and then it goes in a square or circular, a square, or a back and forth pattern. But it goes in, gets stuck, going this way, going this way, going this way. It doesn't matter. It goes in one way. That momentum is kept, and the object keeps moving because of that initial momentum. Fact, happens that way. If you build it, that will happen. Yeah, that's the way it works. Okay, see if there's anything here. Interesting needle example. No, okay, nothing new. But anyway, so it's a way of looking at it. I don't know how important it is. I'm just saying that it's a way of understanding the difference between the force bits, the one-dimensional objects, the elemental atomic bits, two-dimensional objects, and the three-dimensional atom that leads to the creation of all the other big giant things that we consider part of our reality. All right, that's wasn't exactly as I intended it to go, but close enough. All right, so as I pointed out, these, there's certain things, just certain little catchphrases that are important, and I'll keep emphasizing some of them. So the idea is just to think in terms of there's two kinds of things that matter: the force bits, which are all moving the speed of light, and they constitute, when they're at a frequency, we call them light, or electromagnetic radiation. So that is when the little bits have a specific distance between them, and they're moving on somewhat a similar path. The path they're moving on is sort of their polarization, how much variation there is in their alignment would be their polarization. And so their distance between them is their frequency or their wavelength. So they move through space, and when they come out at specific regular intervals of the same distance, then we call that a ray of light or a ray of electromagnetic radiation. And, closer together they are, obviously the more of them you could fit in a little period of time, and the further away apart they are, well, obviously it takes more time for you to see them. But if they're close together, there's lots of them can go by, and anyway. And so it's not really about any kind of intensity thing. It just has to do with numbers. So if you shoot a lot of bullets out of your gun really fast, more bullets, more energy. shoot the bullets slow, bullets have the same amount of energy, but the total energy of your firing will be lower because you pulled the trigger less, less bullets. All right. So when the force is moving at a frequency, we call it electromagnetic radiation, and or light, photons. Now, all these other forces, gravity and magnetism and the nuclear forces, all move at this speed of light. So as I've stated, it really should be called the speed of force, because all the forces move at this speed. And these other forces are doing exactly the same thing. They're just arranged differently. So when there's no frequency between them, no set frequency, then, and they're mixed colors, red and black and random, that's gravity. When you segregate, okay, and force all the little red force bits, okay, to go one way and all the black force bits to go another way, that's magnetism. So a magnet is basically takes gravity that was going to move it anyway, and the gravity goes through it and comes out magnetism. So it's exactly the same force that went in, gravity. It just comes out as magnetism. And because it's segregated, it can now do this charge thing. It can do the, if a proton is in the area of that red stuff, it'll reflect. So if you have magnets with the same colors facing each other, it means that you have the proton heavy or surface. The surface has protons on it, and the surface that has more electrons on it. And so obviously if you're shooting electrons at electrons, they'll just keep bouncing back and forth. And if you're shooting proton force, red force at protons, it'll just bounce back and forth. And that's the repulsion of a magnet. And if you turn it around and reverse that, then you can understand that all the red force, the red force comes in gravity, comes out red. All right. And then it hits this black force. Well, then it leaks out sideways, perpendicular, and it goes out the other side of the magnet. The red goes out the red side, the black goes out the black side. So you get no reflections. So all the red leaks out of this end of the magnet and, gets pushed down that way. And all the black force coming out of this magnet ends up doing the same thing in here, in the sense that hits the red and ejects out this way, and the black comes out the other end. So there's no pressure, and the magnets smash together because of gravity. Gravity is pushing the two magnets together. So that's sort of another key thing to kind of think about it in those terms, that the same force, the same external force, makes planets move into each other and makes magnets move into each other. Magnets do it more stronger because magnets are filtering the force and therefore getting the full effect of the force, where the force is diluted by randomness when it's just gravity. So when it's just gravity, it's yin and yanging. It's pushing and pulling at the same time. And so the force ends up manifesting itself in a much weaker form, and it can't do repulsion. So all it can do is the attraction part, and does it much weaker. But when you do filter it, then you can do attraction and repulsion at full strength, so to speak, at a fuller, more potent manner. But it's gravity that's actually pushing the magnets together, the same force that creates gravity. And it's the same force that's causing the electrons to be attracted to the protons. It's the same force again. It's gravity that does that again in that charge circumstance. And it's exactly for the same, the mechanism between electrons and protons is exactly the same as magnetism, essentially. The force is essentially the same. The manifestation of the force. So the nuclear forces are essentially magnetic forces. All right. I think I said that adequately. But you can see how it all ties together. It is so obvious, in my opinion. You got to concede it looks like a mistake to call gravity bent space and then to call magnetism virtual photon. that must, even if you still believe that, even after listening to me and seeing some of these videos, you've got to have some doubt that that might be a mistake, considering that the forces move the same and that this simple mechanism, even if you don't like this simple mechanism, just realize that this simple mechanism makes it work for both. And that if this simple mechanism can do it, maybe some other simple mechanism can do it. And that you really don't have bent space. And you don't have virtual photons that do, by no explanation, create either attraction or repulsion. But the physicist will give you no explanation for how the virtual photons know when they're supposed to do repulsion and when they're supposed to do attraction. So, I mean, I just don't know how you can deny that the fact that all this stuff moves the same, that it all has a quanta kind of idea of a momentum, that there's a certain consistent amount of momentum that you can extract, and it's heavily related to mass and density of materials, and it's, there's nothing magical controlling it. It's these very specific things controlling how this force affects other forces, how the resistivity of the metal decides how much voltage you can push through it, per mass of it, and all kinds of there's such strict rules about how this force can be transferred through material objects. It just seems so. I just don't know how you people deny it. Don't know how you are so confident in such a poorly I mean, it's very hard to articulate an explanation of either bent space in a three-dimensional model, and certainly no explanation of virtual photons provides any kind of explanation for magnetism. I don't much like this. This is trippy. I don't much like trippy. I'm wondering what your picture is for electrons absorbing a photon. Well, I have sort of already demonstrated that they don't really absorb the photon. The electron captures the photon between it and another electron. So this is a photon. So you see the little squiggly line? That's a photon. It's just force trapped. So you think of these as cue balls, billiard balls. And you can think of the thing trapped as a ping pong ball, whatever. It just bounces back and forth, back and forth. It just keeps reflecting. And obviously with each reflection, it's imposing a pressure on the object it hits. So it's pushing these two things apart with each impact. And if I bring them closer together, there's more impacts. Same number of ping pong balls, but there'll be more impacts, which means more energy. So in a sense, proximity equals energy. Pressure equals energy. So that's how you store energy, is just compressing electrons. But it takes energy to compress them. You have to create more energy to push them together. So you have to put energy in to get energy out. And that's what the sun is doing. Essentially, gravity is pushing all the little bits into each other, so to speak, into one center, and creating a great deal of pressure. And the pressure is getting locked in because of the formation of atoms. The atoms are essentially a way of locking the pressure. It's a configuration that's stable. So any stable configuration of electrons around protons has to be created in pressure. And once you create it in pressure, it holds its pressure. That is, it keeps it. It doesn't leak out of it. and that's a stable element then. And that atom can survive in space for a very long time. Now, some of them decay and fall apart because, yeah, they're losing too much pressure. They're leaking because they're not perfectly constructed. Their geometry isn't perfect, and the pressure doesn't, the little ball, ping pong balls, every now and then they're flying out. Okay, they're escaping. And that's your radioactive isotope that's falling apart. All right. Okay. All right, it explains heavy planets having magnetic fields. Now that's more complicated. Is the magnetic field to create the magnetic filter. So you have to understand the magnet is a filter and has to be made a specific way to filter. It has to have electrons and protons in specific arrangements, in a specific arrangement, that is, for it to be able to filter the force. That is, for the force to reliably come in one way. Red force comes in this way, it goes this way. Black force comes in down here, it goes this way. It has to be a specific kind of configuration for it to be a good filter. So it's not just as simple as saying everything gravitational will be magnetic, because it does in fact require there to be a certain kind of movement of like charges, so to speak, like force. You have to move the force to move electrons in a specific way to create more of the force radiating and all that. I'm just saying it has more to do with the fact that you have to move atoms in specific geometry, specific straight lines even, to be able to excrete the filter effect to magnetize the atom. An atom isn't just always magnetic. I guess it's a simple thing to say. It takes specific kinds of atoms, and they have to have a specific amount of pressure in them. Anyway, instead of them having molten cores, they all have molten cores. So I don't think there's anything bigger than our moon has a molten core, in my opinion. You won't find anything in the universe that doesn't have a molten core that's as heavy as the moon, that's as dense as the moon, that is heavy for its size. So anything that dense is going to have a molten core. Now, asteroid, no. But anything bigger than the, like I said, I already said it. See, it's all about pressure. So you have to think about every single layer of atoms. They're all still accelerating. So every layer of the Earth, every layer of me, you could think of each one of those layers is still being accelerated by gravity. That is, it's still going that way. And it's going that way against atoms who are already being pushed back up the other way. They can't go that way for free. So they can only go that way and then get pushed back up this way. So they're constantly creating pressure. And so for every single layer is weight, is real weight. So you could just imagine what the weight is at the center of the Earth, or the center of the moon for that matter, right? I mean, it's 1,000 miles across diameter. I don't know what the diameter of the moon is, but whatever it is, say 500 miles. So you have 250 miles of, yes, semi-heavy stuff sitting on top of it, all still accelerating at 60% of the Earth's gravity. I mean, it's still a huge amount of pressure. All right. And that pressure equals heat equals melted. You just can't avoid it. Okay, thanks. So it's just radiation in reverse. I'm not sure what that is. The force comes in and bounces around. Sometimes it bounces around, but I mean, the point is it can get trapped. And when it's trapped, it's not heat, it's not any kind of problem, but it's pressure. Okay, it's a real thing still moving. But until you release it, the pressure, right? The pressure is harmless until you release it. So you can't tell something's under pressure until you release its pressure. That's why it's so funny about how atoms are so benign, right? They look so benign. Look at this pen. It can't hurt a fly. But we know there's enough pressure in this pen, you know, that if I released it all at once or very rapidly, that it would blow up the planet. You know, and that's the real interesting thing, right? I mean, the pen isn't hot. The pen isn't doing anything that would indicate that it has enough megatons of explosive power inside of it to blow up a whole planet, but it's in there. And it's all caught in nice little benign traps. And it's not leaking any radiation. It's all stable atoms. And so they're doing nothing harmful, nothing to indicate that they have been in the center of a sun somewhere under huge pressure to create those atoms, and that those atoms are essentially batteries. Okay, there have been batteries made by the universe over billions of years, and there's a billions of these little tiny batteries inside of this pen. And if I release the voltage, the pressure, the voltage out of those batteries all at once, it'll blow you to bits. Now we have a Dick Woodman again. Anyway. All right, it bounces around, and that's why it's only absorbs certain energies. Thanks. Why it absorbs certain energies is another side. That's a little more complicated. How you what energies will be absorbed by an electron without it rejecting it? So the atom has to stay stable. Now it can't absorb certain pressure and stay stable. So it has to do a conversion or something else. So like an infrared could come in and it shoots out an ultraviolet can come in and it'll shoot out an infrared. Okay, and it can keep the rest of the pressure in between the electrons. But you know, there'll be some sort of conversion because it can't hold the pressure in the atom itself in that original form. But anyway, I don't want to get too complicated. Hey Gary, have you heard of rice being alarmingly high in arsenic? Well, what's alarmingly high? I mean, lots of food has lots of heavy metals in it. A lot of that's getting worse in some respects, just because people are growing food in shittier places. I don't even know if that has something to do with the rainforest, actually. Because that's not very good soil. Rainforest could be lots of heavy metals in a rainforest. But anyway, what do you think? I don't think heavy metals are as scary as people think. So you need a lot of arsenic to start. And there's nowhere near that much arsenic in the rice, I don't think. But I don't like, I would like rice to be just rice. I would like it without arsenic. That would be really cool. I like everything not to be dirty and full of shit. So I think it'd be nice to have stuff that doesn't have shit in it. Yes. I asked because you once said you eat beans and rice every day. No, I don't eat them every day. I eat pasta, rice, potatoes when I can get them reasonably priced, and beans. Those are the 4 things I eat. So I eat rice one day, and then I eat pasta another day, and then I eat potatoes another day, and then I eat beans another day. Yes. With bread. So I make bread to have with my beans. Anyway, yes, I like potential energy. But it's way off subject, Dick. Just way off the subject. Yes, like potential energy. All energy that's not free, that is, it's not in the form of gravity, let's say, is essentially a form of potential energy. All the force bits, you could argue, are free. And everything else, all the matter, is potential energy. Why should the absorption of a single photon elevate an electron to a higher orbital if the photons within the electron are already moving at the same constant speed. Well, they're not moving with a constant speed in the sense of they're not trapping momentum. So I, again, would argue you can't think of the electron as having force bits that are actually moving. They have force bits that are in some way neutralized. So it's like two force bits would hit each other and get stuck. And so they wouldn't really be moving anymore, but they could still be exchanged, and you could have these two force bits stuck together instead. You know, so you could have some other arrangement, if you get my drift. But they don't really go anywhere anymore when they're matter. When they're matter, they have to be neutralized, or matter would have its own will, so to speak. I mean, electrons. And electrons don't have their own will. Electrons only move when you push them, while you're pushing them. When you stop pushing them, they stop moving. So I think you're just going to make it too complicated to say those kind of things. But obviously the pressure is the important part. So the orbitals, in my opinion, the high pressure orbital and close to the nucleus, that's where the highest energy is. The further out you go, the less energy that's in that orbital. So you're really talking about pushing electrons in, not pushing them out. Okay, so it's always about more pressure. So it takes energy to push an electron from an outside orbit to an inside orbit. That you can sort of understand why you would need extra energy if you had 5 magnets, all right, and they're perfectly balanced. You know, they're all heads up, and they're perfectly balanced to a heads down magnet in the center. Okay, so it's a magnets. So these are all north up magnets here. Okay, and in the center there's one north down. All right, so you can sort of understand that these little magnets want to all get to the center, but they can't get there because they're repelling each other. So they're in tension. And the idea is you're going to knock an electron from this place where there's distance, you know, this much distance between the electrons, to a place where there's only this much distance, which means the electrons are a lot closer than they want to be to each other. And they're a lot tighter, angrier, essentially, in that tension. But they're also more attracted to the proton. So they're in the strong attachment to the magnetic attachment to the proton, and they're in a strong hatred for each other. And so it takes energy to push one from out here into in there. Because of the fact that, see, I could draw it, but no, I'll draw it on the back of this thing. What the hell? Oh, my nail fell out of my... I should get the tablet out. Yeah. All right. So you have... I think I can just do it with 3. All right. And so when you have them further apart, there's further distance. Okay, that should be enough for you to get what I'm saying. All right. So you can understand, you get these 3 down here are on the inside orbit. These 3 out here on the outside orbit. You see how far apart they are. Okay, lots of distance. These are really close. That means these had to be pushed in because they don't like each other, electrons. Electrons repel each other strongly. All right. And so the idea is let's say you have a spot here, you can push one in and create more pressure in here. So first you understand that if I'm going to try to push something in here, I have to, let's say you're going in this way. You have to overcome the fact that now there's greater pressure because these are closer together. So when you're pushing in, these are going to be resisting you strongly, okay? Because their partners are saying, no, 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 you cannot move towards me. You cannot move towards me. And so there's going to be a great deal of resistance to pushing that new electron into that new location. So you can understand that it takes more energy to push into that tighter orbit than the amount of energy you'll get back when you release it, technically. So it costs more to put the energy in the battery, okay, than you get back out of the battery. And it's a way of saying it. You have to spend more energy. It's not like you don't get it back as heat. You get it back as heat. But the point is you have to put in extra to create to get the 8 more points of pressure inside the atom. You had to use 10 points of energy to get it in there. And there were 2 points of heat released. All right, that's probably enough. Elevated electron to a higher. Okay, so I think I did that. Okay, more photons equals more bounces. That's also true. So the more ping pong balls between 2 paddles, the more pressure on the paddles, right? So if I have 10 balls bouncing in between 2 paddles, that's going to be more pressure than 5 or 2, right? So if there's only 2, then these 2 paddles would be able to get really close. But if there's 10, they're going to be further apart. So you either increasing pressure by proximity or by amount. Now, I don't want to get into any kind of hard discussion about which one dominates atoms, because I would almost argue that atoms don't allow extra photons in. They only allow you to create more pressure. So that becomes a little bit complicated. So I don't want to get into that argument. But clearly, yes, it's true. More photons equals more bounces, which equals more pressure. Also, closer proximity equals more bounces, equals more pressure, more energy. Oh, okay, thanks. Okay. So I'm caught up again. Very good. Oh, I'll get this paper back. That's my notes on it. All right, so I did the one-dimensional, two-dimensional, three-dimensional thing, so that's good. Atoms are three-dimensional, did that. Oh, God. Have momentum on all 3 dimensions. Yeah, did that. All 6 subdimensions. Did the 6th, yes, did the subdimension thing. Is universe evolving into heavy atoms? I love that. I brought this up at a video, I don't know, the last one, the one before it, and something I've never even actually thought of, and I just said it in the video. But the evolution of atoms is sort of an interesting subject because nobody really thinks about it like they think about the evolution of organisms on Earth. But the truth is that the evolution of atoms could be doing exactly what biological evolution does, which is over time, it favors complexity and the storage of energy in more and more secure vessels, bigger, generally speaking. And that the same thing could be happening in the universe itself, in the sense that there's essentially a competition between the 100 or so elements in the universe, natural elements in the universe. And over time, there could be ones that are winning in that race. That is, carbon, for example, might be being produced in the universe at 10 times the rate it's being destroyed. That is, atoms are being broken into something smaller than a carbon atom at a much slower rate than how fast smaller atoms are being put into carbon. And you could say that about gold and all the heavy elements. And so essentially, this is almost a thermodynamic argument again, too, where the universe is essentially creating batteries. It's storing its energy in heavier and heavier atoms over time, because they're winning this evolution war. And so the universe will eventually run out of hydrogen, go stone cold, because it won't be creating helium, and suns anymore. And in a sense, so you go through this whole thing about what wouldn't be happening anymore. Now, you'd still have big objects that are creating tremendous pressure, so you might still be making atoms. You just won't be making helium, And so that could get very interesting, because the heat of the sun is essentially, the radiant heat, the heat we feel, is mostly being produced by the leftover bits from the conversion of the hydrogen atoms into helium. And if you didn't do that, you could still be converting other elements. You're just not making the little bits that fly off. I still argue the sun would be really hot inside, even if it wasn't burning hydrogen. Even if it wasn't fusing hydrogen into helium, it would still be hot as hell. The fusing of hydrogen into helium is just one version of a fusion. It's doing other fusions. It's probably converting helium into lithium and lithium into carbon. It's probably doing some of that. And all of that stuff isn't what makes it hot, because it was already being made hot by just being so huge and creating such gravitational pressure. So that's the sort of interesting thing, is you don't necessarily need to be, you could have a very heavy object that is a black hole in the sense that it's black. It doesn't radiate heat because the heat doesn't get to the surface. See, I mean, if the Earth wasn't in the sun's presence and the atmosphere wasn't warmed, it would just turn to ice. And everybody thinks that like ice is really cold, but ice freezes at a really high temperature when you think about it. And so the Earth is still really something that is covered in ice can still be incredibly warm relative to absolute zero. So I mean, relative to absolute zero, this stuff that we call cold is really, really hot. I mean, it's really quite warm. I mean, the fact that water is frozen doesn't mean much, because water freezes at an incredibly warm temperature. And we just don't think so because of our prejudice, because all the other metals only turn into liquids at such high temperatures. It makes us think, okay, that water only turns into a solid at a very cold temperature when it's still a very warm temperature. The natural state for all of the elements is a solid, essentially. So, yeah. All right, it would be amazing to see your theory explain why the heavier atoms are unstable. Well, they're not. Most of them aren't. I mean, and they all have unstable versions, though. So the heavier they get, the more likely they are to have a version of them that's unstable. But you can understand why there'd be a bad version. The bad version would be it has too many electrons, or it has too few electrons, and therefore, all of that tension is not perfect anymore. The geometry is no longer perfect, and a few of those ping pong balls are flying out. And as they fly out, it starts to lose pressure. And as it starts to lose pressure, it expands a little bit. And as it expands, it starts to degrade. And eventually, it splits into two nucleuses. Okay, let's see. Heavier atoms are unstable and can only exist for nanoseconds in the lab. Well, again, those aren't even those aren't even natural elements. So I don't even know why we'd even argue about the synthetic. What do you call them? Not ions, but isotopes. Because they're just broken on purpose. That's like just sitting there smashing a rabbit in the head with a hammer and then saying, "Look, it's dying." Yeah, duh. You hit it with a hammer. It's going to die now. You break an atom, it's going to die. They're too unstable for all the pressure. Okay. Well, I think my theory does explain that. But it's the number of protons that make the element what it is. Yes, and the number of protons just create the amount of charge. And that's all the density of the charge is what decides the position of the magnet. So if you have a weak magnet in the center, you can't hold the tension for the other magnets, and the whole thing just falls apart. So it can only work if there's balance between the attractive pressure towards the protons and the repulsive pressure between the electrons. And if those two pressures aren't balanced, then the thing falls apart. They're semi-delicate in the way we imagine them, but clearly they're quite durable. So when in these right forms, when in the form of a piece of carbon, they're pretty, well, carbon's probably a bad example because it does have isotopes that do well, they die so slowly that it's probably not a great example of a dying. I mean, obviously, they each atom doesn't degrade every day. You know what I'm saying? It's just 1 in a million of them loses a ping pong ball every day. You know, that kind of thing. All right, but it's the number of protons that make an element what it is. Yes, well, it can afford, as we know, through ions and through the chemistry, it can afford to be missing an electron, but it can't afford to be missing too many protons. That is true, in my opinion. But the neutrons are also what's holding the neutrons wouldn't be held together without the protons wouldn't be held together without the neutrons. The neutrons provide the conduit. So 2 protons can't get close to each other unless you put an electron between them. So you can sort of understand that's what the neutron is doing. The neutron is essentially putting an electron between 2 protons, which means all the reflective force from the protons leaks out of the electron, and therefore the 2 protons can get really close to each other. And that works vice versa. Electrons can get closer to each other, like a hydrogen atom or a helium atom. The electrons can get very close to the nucleus if there's a proton there in the middle. And so if the 2 electrons are on opposite sides and they have a proton between them, they can get really close to each other. Now, if they're this way, you know, perpendicular to tangential to each other, then their reflective force will push them away from each other. But if they're on opposite sides and a proton in the middle, they can get very close because all the pressure leaks out. Yeah, so we've done that part before. All right. So anyway, I thought the evolution of the thinking, see, I never thought of it that way. I never thought of the periodic table as a Darwinian tree, okay? And it's basically just a kind of evolution, the evolution of batteries. And so the atoms are batteries. They're evolving in the universe, and there's probably clearly statistically the universe is becoming more one kind of section of that periodic table than it is the other sections. It is going to be just like mammals cover the earth. There's going to be a winner, and it's going to cover the universe. All right. Gravity old. Okay, that's always good. And gravity new. Okay, so this is another complexity in the gravitational argument. That, you know, somebody they bring it up as the heat argument when you're talking about mock gravity, and I've already dispensed with all these silly, stupid arguments. All right, so the idea is that, all right, you could sort of understand that if this is a spherical object in space and the stuff is still accelerating, each little atom is being accelerated towards the center, all right, that you have like an equal amount of stuff absorbing force. So for these atoms to move, the atoms have to absorb a piece of energy. So if you thought of it as fish moving, they have to catch the fish and trap the fish in a circle or something. So the fish has to come in and they have to trap it so that you trap the momentum. So the fish had a momentum. It was going this way. It gets caught. So it doesn't keep going this way anymore at the speed of light. So it doesn't go where it was heading. So it doesn't hit the thing over here. So if you have 2 objects here, so just imagine 2 of these, and this one is caught the fish going this way. That is, an atom moved this way towards the center of this thing's gravity. The atom absorbed that fish. That means the fish didn't come out here and go to this other one, didn't hit it, okay, couldn't get absorbed, and therefore more fish hit this side, and now this one's going to absorb a fish going the opposite way, and it's going to move towards this. And when it absorbs that fish, though, that means that fish didn't hit this one, and so it's going to do the same thing. It's going to absorb more fish going this way. There's more fish will hit it this way than hit it this way, so it's going to absorb a little fish going this way, and so it's essentially inductive. As one thing absorbs energy in a direction, the other thing feels the lack of pressure, moves into it. To move into it, it has to absorb energy. It means that energy doesn't hit this other thing because you absorbed it. And that's essentially gravity. Now, the catch is that, say I just throw something, I throw a little piece of, it's so hard to say it, because one little piece of matter won't matter. But I throw a little collection of sand into space, into just a little round space, just a little bit of blob of sand. And this little kernels of sand will all start moving towards each other, okay, through this process. Let's see. Well, you can sort of understand that as they move closer and closer, and they get tighter and tighter and closer, now they're going to start pushing on each other, creating heat and pressure. At some point, it's all equalized in a sense that all the internal pressures are even. Just as many pieces of sand will be going this way as pieces of sand going this way towards the center of gravity. So it'll just turn into a sphere like the Earth. There'll be just as much atoms moving from Fuji towards me as moving from New Jersey towards Fuji. And so it becomes nothing. There's no gravity because you're absorbing as much energy this way as you're absorbing energy this way. So the net effect is let me see how to say it. You don't absorb the energy perpetually. Yeah, that's the catch. You can only absorb the energy per your density one time. So once you capture a velocity to move, when the pressure pushes me back up, okay, so I get accelerated into the Earth, and think about it like a trampoline. I dent it, and then the Earth pushes me back up. And when it pushes me back up, it had to absorb energy going the opposite direction than the energy I absorbed. But the point is to do that, I had to release the energy, right? So when I go this way, I always have to leave that way behind, right? So there's always the reflections, which you're essentially talking about. So when the force pushes me down, it reflects back out. So in a sense, gravity becomes a neutral once it's absorbed all the energy. And once it's once it's as small as it can be. Once its pressure is to its maximum extent, it can't get any more pressure, and there's no more matter to hit it, it can't get any heavier, then it's just stable. And so has the stable thing still have gravity? Well, it still has gravity only because of randomness, Brownian motion. So technically, at any one moment, there's more Earth, right, going down towards Fuji than coming up from Fuji at any one moment. And so essentially that Brownian motion means that the gravity is on, off, on, off, on, off. That is, it's push-pulling. So when something enters, at any one moment, there'll be a point where it'll say, I'm going this way. And no, I'm going this way towards you. So at any one moment, it might, so say this pen just pops into space next to this thing, and this thing's Brownian motioning. Well, at any one moment, it's going to be going this way, and then one moment it might be going that way away. But when it's going towards, that will be a real absorption. That means real energy got absorbed, energy will not hit the pen, and the pen will now move towards the magnifying glass. Now, at the very next moment, this Brownian motion means it's going to move away. And exactly the opposite thing will happen. But what does the opposite mean to this pen? When this thing absorbs motion away, that doesn't mean anything to this pen, because that energy had already left past the pen. It can't affect the pen. See, absorbing energy this way can't affect the pen. The only way you can affect the pen is moving towards it. So the only thing the pen is going to feel is when you absorb energy going this way. If you absorb energy going this way, the pen won't notice. So all it feels is this motion. It doesn't feel this motion. So that's why it induces. And the point is even if it did feel it, even if it felt the going back this way, even if there was a way that could possibly affect the pen, going away, See, obviously going away is absorbing stuff that won't ever hit this pen anyway. That's absorbing stuff that already went through the pen. So why would the pen care if you absorb stuff that already went through it? The only stuff that can matter to the pen is the stuff coming towards it. But the point would be is that in the end, it doesn't really matter, because what's really going to happen in the end is just going to be the net effect is every time this thing moves, it absorbs force that was going the speed of light, and the force won't hit this at the speed when it should have. It's stuck here, moving the pen really slow. So the speed of light is really fast. The pen moves really slow. The pen absorbs the thing moving very fast, owns it. It doesn't get to this surface. This thing moves towards it. When this thing moves towards it, it's absorbing energy that won't get to the pen, so that's still going to work. So that's a long way of saying it, but it's really just important to understand the pen. All the pen can notice is when something moves towards it. It can't notice when something moves away. Gravity only works this way. It doesn't work when this thing moves away. The pen won't know. It'll know that this is missing. Okay, it'll know that nothing's moving towards it. Okay, as this gets further away, this can't move towards it in a way that is anywhere near as strong as when it's really close. And so the further away it gets, the less it can affect this pen because of the way the gravity spreads in lines like this. So clearly, it can't affect the pen the further away it gets, but there's no direct connection in the sense that this was direct. When you absorb the energy, you directly affect the pen. So absorbing it directly affects it. Moving away doesn't absorb energy that can affect the pen. That's energy that's already gone past the pen. All right, well, it's physics, so it's going to be you have to do a little bit of thinking. All right. So I think that's my list for the day. So if you have anything to add or blah, 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 fine. And if not, I'll call it a day. But yes, this, it explains so much. And I shouldn't have had, this shouldn't take 7 years. It's like 7 years I've been doing this or whatever it is now. It shouldn't have taken this long. And it looks like there's no evidence that it's not going to take me another 7. And people should be catching on by now that this has got to be the right answer. It just works too good. It answers too many questions, and it answers them so well. I don't see how reasonable people can deny. This is like evolution. It's like the theory of evolution. It fits too well, and it's so much better than that God babble. And this is so much better an explanation than that stupid wooey Heisenberg, Huygens, two places at once, entanglement, antiparticles. It's so much better than all that slop. So yeah, well, I've got it. I've got it in my head really well, and I do have to fix the website because some of what I say there, it just isn't right. But the drawings are mostly correct, and most of it is correct. But some of it needs fixing. And it's not one of it just happens to be not one of my skills in the last couple of years writing. I don't know why. I guess I'm just wanting it to be. I want it to be concise and complete, and anybody could understand it. And that might be expecting way too much because it is physics. And as I was just trying to explain with this gravity argument, it's such a subtle thing to understand, that this pen can't sense stuff once it leaves. It doesn't care what happens to it. When a force leaves this pen going away from it, it has no knowledge of what it does. It couldn't care less what it does. It cares that this thing moves further away from it, don't get me wrong, but it can't sense the force. It can only sense force coming towards it. and things that are affecting the force coming towards it. So only things that affect the force coming towards the pen can be things the pen can react to. It can only react to this side of the Earth absorbing energy. It can't react to this side absorbing energy. It's that kind of weirdness. You know, when the moon is moving towards the Earth and all that stuff, it's really the backside of the Earth is what's really holding the moon. Kind of. You know. That's the only side that matters in terms of what's really producing the force change that's keeping the moon in orbit, is the dark side, so to speak. The opposite side of the Earth is where the matter's doing something that's making the moon fall towards the Earth. If the moon was above me moving towards the Earth doesn't mean anything to the moon. Couldn't care less. That gravity isn't doing anything. That movement isn't doing anything. Oh, you beat me to it. Well, technically, I don't know. It might have been a tie, but yeah, I guess I did. Obviously, it was the next step in the argument is the realization that this dimensional thing always shows up in these subtle little ways, and it's really only half the dimension that matters. You know, so in a way, we sort of cheated dimensionality by saying the 3 dimensions. You know, because it's the 6 sub-dimensions are really important. But dimensions will get interesting too, right? Because two of the dimensions in the 3 dimensions are always on the same plane. You know, they're always, 2 of them are doing the same thing, like up and down and left and right are doing the same. They're on the same plane, the same flat plane. And there's always 1 dimension that's off the flat plane. So there's always 2 dimensions on the flat plane and 1 dimension off the flat plane. And that's sort of an interesting little factoid. So, but anyway, this is just such, like I said, this theory is so good. Just, I wish somebody else was saying it. I wish I didn't have to say that. But I mean, it's just so fucking good. I mean, I wish somebody else came up with it so I could go, oh, fuck, that is so fucking brilliant. You did it. That's fantastic. It's amazing. Now I have to do it. It's just annoying, you know. It's like I said, it's these arguments. The argument was always good just because the argument against conventional physics is so good, just even without even without evolution, the theory against God is still a great argument. Okay, I mean, all the arguments against the existence of Jehovah are still great arguments. Like, it's a 2,000-year-old made up fish story. I mean, it's absolutely no evidence of a God, no fingerprints, he doesn't write his name on trees. Who the fuck is this idiot? Why doesn't he talk to any of us in fucking English, for fuck's sake? What is he, retarded? He thinks we're supposed to know stuff without him telling us anything? Goddamn asshole. Why didn't he tell us about penicillin? Why doesn't he tell us the obvious, the fucking cunt? I mean, the arguments against the existence of this stupid creator is so fucking good, even without evolution. But then you start piling on Darwin, and then you pile on chromosomes and DNA evidence and geological evidence and all the fossils. You start piling on all this fucking evidence. How can you people live in denial? I mean, seriously, how can you call yourselves intelligent to still be resisting after all this? Come on. I mean, you should have been ashamed just from the beginning saying the words Heisenberg and Huygens and de Broglie wavelength. Yes, electrons, even though they're, it's like cars have a wavelength. You're going 60 miles an hour down the road. De Broglie says you have a wavelength. I mean, what a pile of horse shit. You can say that anyway. I don't know what that means. Nope. So anyway, a little more interaction, people, or it'll be time to go. Questions, comments, something, blah, 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 blah. Some explanation why you are resisting. Why do you resist? 20 viewers, not bad. Pretty dead comment section for 20. Let's see. Yeah, same thing. Okay, nothing new. All right, 2-minute warning or whatever. Okay, good night. Yeah. All right. I try not to resist. Okay. Resist. Oh, well, I got it. I probably spelled it wrong anyway, also. But I'm just saying, it just seems to me it's a substantial pile of evidence I have presented. The very fact that my theory unifies so simply and easily. I mean, it does it easy. It does it without even trying hard. And unifying is, Einstein went to his grave looking for this. I mean, he would have loved the simplicity of it. He would have just loved it. Even if it kills bent space, he still would say, oh, yeah, that's just so much better. It's not quite vaping very well. I'll switch over to my stick instead and see how that's doing. That's a little better. Thank you. Let's see. The dark side of a petrified futonary perspective. Whatever. Is that supposed to mean something, Ed? I mean, that's some sort of counter argument to something I said in this video somewhere. Ed? Ugh. I mean, that's the other amazing part is that if there are any arguments, they're so fucking bad. I mean, they're just so bad. Religious kooks come up with better rationalizations for their nonsense. I ain't related to no minky. Even that's a better argument than this mush. I saw this documentary about the battle between Einstein and the QM guys. Yeah, well, like I said, Einstein opened the door to the problem, but anyway, how on earth can these people want the universe to make no sense? Yeah, well, so Einstein got pretty humble towards the end. I mean, 2 years before he died, he said, I've spent 50 years thinking about photons and I haven't advanced my knowledge one iota. It's a pretty humble statement to make after, basically saying I knew just as much about photons 50 years ago as I know now. They're fucking weird. And like I said, he did really go to his grave really wanting, this kind of mechanical system. He wanted something this clearly. He thought the universe was just as I'm arguing for, something just incredibly simple and mechanical. It was, and like a pendulum swing or something. I don't know how to what to metaphor it to in nature that isn't a complex thing, but I mean, it all looks complex from where we're sitting, but it's just a checkerboard. He wanted something that simple. 4 simple rules. Speed of force bit, matter bits, charge, plus, minus, that's it. Red, black, whatever you want to call it. Square, round, that's it. We're done. But yeah, it is. And quantum mechanics just gets wackier and wackier. They just keep going further and further, down bizarre roads of idiotic speculation. Like even Feynman did this, where they theorized that it could be possible that one electron is the only electron in the universe, and it time travels to every location in the universe. I mean, what? I don't even know how to say how, that's just worse than whoever invented the Holy Ghost, right? I mean, you're just saying, okay, you got Jesus and God. That sort of makes sense. Okay, whatever, Father, Son, blah, 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 blah. Who's this Holy Ghost asshole? What the fuck is his role? What idiot thought that up? Who thought up the Holy Ghost? Yeah. Well, Michio Kaku is just so. I mean, he keeps talking like he invented string theory, and if like you go to the string theory page, he's not mentioned anywhere. Anywhere where I've seen anybody who's done any real work on string theory, it never says, "Oh yeah, Michio Kaku did this great." No, there's nothing. The one electron universe was Wheeler Feynman's friend. Well, I know, but Feynman used the example of it a lot. And Feynman thought it was cool to think about, but probably not real. I know, I'm just saying, though, he actually did do Feynman diagrams using this idea of a borrowing energy from the future. So you make an event happen by borrowing energy from the future, and then you give the energy back in the future. See, at least Feynman sort of understood that they had a real problem with energy. But he solved it in that kind of silly way, right? So it's basically saying that, yes, I'll borrow gravity energy from the future. That is, the center of the sun is hot and it's making nuclear things happen. And so I'll borrow that gravity energy to make gravity in the past. So I'll make gravity in the past to create that pressure. It's just so circular. And Feynman did that shit, and that's just that's kind of creepy. Now maybe he just did it because he loved playing with math and doing all kinds of silly, creepy stuff. But I'm just saying, that's just creepy to even. Oh, that's creepy to even do. In the closet. That's a really dirty way to jerk off. Yes, creepy physics. So look, it all seems creepy to me. I'm sorry, it always did. Like the minute they did this stuff with the photon, photons are doing this and this. What are you talking about? How do the photons know how to do that? I can't do that in a swimming pool. How the fuck does a photon know how to do that shit? Come on. A photon, a dumb little fucking moron photon. What does it need to do all that shit for? Yeah, this photon. Feynman sort of was the whatever the bishop of physics. He's a bit of a child, a bit of an electron molester. Yeah, damn fucking physicists molesting poor little electrons. You're saying Michio Kuku is question mark. Is full of shit. I'm saying he's horrible, self-promoting, self-aggrandizing, butt shit. I hate him. He thinks he's like Einstein's. I was like Einstein's best friend, because he read an Einstein book. I can't stand him. Shit. Wow. Hey, get your last shots in here, people. Come on. Come on. I can only, use up so much of my own energy. I need a little bit of feedback. I meant to ask Dick Woodman that. Oh. Yeah. No, well, I'm just saying that, it's, all the talking heads of physics, they all have personalities. They all have a certain shtick that makes them, sort of interesting people and all that kind of crap. But they're really not accomplished physicists, which is kind of the funny part, right? All the talking heads of physics are not accomplished physicists. So they're, they just talk the shit. They don't actually make the shit. So Feynman was an exception. Feynman actually did some physics, but I would argue it's kind of garbage physics. Feynman diagrams are nice simplifications, but that's just pattern. He was just finding a way to make the math, the explicit math for a pattern, something you could see, rather than have to see as like I could write 1/4, or I could just paint 1/4 of a battery red, and which one says more, obviously the images say more. So, understanding that with the progression of time going around a clock, that if you have something that's a periodic event, that something always happens at 1 o'clock, something always happens at 2 o'clock, something always happens at 3 o'clock. And if you just go around the clock and you're going to stop at some point, over time, if you randomize where you're going to stop, you'll always stop 10% of the time at 1 and 10% of the time at 2 and 10% of the time at 3. Well, Degrassi Tyson, I think, is he's the most hypocritical. The most duplicitous. The guy I've caught saying exactly the opposite thing more times than any of the others. 1 minute he says, "Oh yeah, life evolves in the universe every millisecond because there's carbon all over the place." And the next minute he says, "No, most of the universe is totally inhospitable to life, and no, it couldn't survive a millisecond there." He's just, I don't like him. Well, I don't know. I don't, that's sort of a rough standard to say that people can't be a little chubby. Life is tough, and, I have my vices too. And I've made my errors in my life, and sometimes people just get caught up. Once you get fat, it's so hard. It's like once you make pressure in an atom, right? It's a little hard to let it get it unpressurized. So once you create a circumstance, it can be very daunting to get yourself out of the mess you can make. So I do understand some of that. Not that I'm not awful cruel sometimes myself, but I'm just saying, yeah. The worst is Christian apologetics. Well, I'm just sort of arguing that no, you want to find something worse. Find a physicist rationalizing their entanglement bullshit. That's worse than Christian apologetics. They have universities where they learn to debate and maintain their nonsense. Yeah, well, I'd argue that all the universities are full of professors who will never expose themselves to somebody who can interrogate them. I haven't found a physicist yet. Have you seen the show yet where the physicist says, "Go ahead, interrogate me, interrogate my physics"? No, doesn't happen. Well, I'm just saying some of their bullshit explanations, like Ken Hovind could say something like, "Oh, yeah," you say, "Well, why are there dinosaur bones in the ground?" And he could say, "Well, because God's testing you, you idiot." It's kind of obvious, right? He's saying, "Look, I'm going to do some things that are going to confuse you. And if I wanted you to have all the answers, I would have given you all the answers." The whole point of the tree of knowledge was because knowledge is dangerous and knowledge isn't suitable to your egos. So it just doesn't work for you to have knowledge, because once you have it, you'll abuse it. And so, he can make some sort of rationalization. And that makes a hell of a lot more sense to me than, talking about how photons split in half and read our minds and, do calculus. I mean, I could just keep pointing out how the lens is the wrong shape for gravitational lensing. The lens is the wrong shape. It's bending light a little, and I could just point out stuff like that. Why did Einstein take the squared off the inverse square law for photons? Why? The photon thinks it got there instantaneously. It didn't think it was in the gravity longer. It thought it was in the gravity less time from the photon's perspective. Why is it getting hit with less gravity? I mean, more gravity. How do you convert solar masses into bent space? Right, LIGO. How exactly do you do that? When did Einstein propose that as being a possibility? You do it posthumously somehow? Yeah, well, you got to be careful saying LIGO, because then you're making accusations. I don't know if these people are. It's like saying the religious people are lying, and some of them obviously are lying. I mean, they create fake evidence and make completely false. I mean, they know the evidence is wrong, and they know that was faked, and they still argue it, and so there are clearly liars. And it's hard to say what the LIGO people are doing exactly, just because they're certainly embellishing, and you could argue way beyond reasonable. I mean, I'd like them just to explain, now that I've diagnosed the interferometer, at least, tried to deconstruct one. I'd love for them to explain how the damn thing works. You know, where exactly does this interference happen? Where does the single photon take both paths and then recombine? Where does that exactly happen? Or how does that exactly happen? How's that beam splitter exactly work? You know, how's exactly, is it really creating two equal beams, or is it filtering the light? And the filter is creating two different beams of light, not two same beams of light, two different beams of light. Yeah, we'll keep at it. Pieces at a time here. Well, if they claim to come up with the nothing, they get no more money, and who is going to reproduce it? Well, that's the truth there. I mean, they certainly have some very negative incentives to LIGO, you know, to create evidence where there really isn't. And you know, they had a huge incentive to come up with something, and you know, that's very dangerous to create science that way. I mean, to give your scientists incentive to fudge the evidence, it's a very dangerous thing to do. Like giving the internet to Google when it's a marketing company. Very dangerous thing to do. It's like giving the card catalog to Barnes and Noble at the library. Just wouldn't be the smartest thing to do. All right. So I guess I'll toddle off. So thank you for the participation, and appreciate the trolls seem to have taken the night off, which is also appreciated, and such. So till next time, I got a. You know, I did show you some video earlier, but I do have a bunch of stills of some other needle experiments. You know, with the two slit stuff. But again, I haven't found anything. I haven't got a knife yet to stick in its throat of the wave theory. So still looking for a way to create an experiment that creates a decisive answer, and I haven't found a decisive experiment yet. So I have to keep fiddling around. But anyway, till the next time and such. Yeah, it's probably enough. Last chance. Nope. Okay. Till next time and such.